young scholar. I hope your recently acquired knowledge of surface area and volume of different 3D shapes is helping you to better understand the physical world around you. The shape that we are discussing today is something that we see almost every day all around us. In fact, the world we live in resembles this shape. Yes, we are talking about spheres. So, let's take today's video to understand spheres better. Since we see enough examples of spheres on a regular basis, we don't really need a definition for them. What we do need to know is how spheres are formed. Quite similar to how we form right circular cones. Yes, we take a right triangle and then rotate it about one of its non-hypotenuse sides and we get a right circular cone. So, what shape do you think when rotated would form a sphere? Correct, a circle. A circle when rotated about its diameter would form a sphere. But then, this sphere would obviously be hollow inside. So, how do we form a solid sphere? Simple. We rotate a circular disc instead, and voila, a solid sphere is born. You must remember though that the word sphere is generally used for a hollow sphere, like the surface of a ball. We use the words solid sphere for a solid whose surface is a sphere. So, now that we know how spheres are formed, let's learn some of the basic terms related to them. The basic terms of a sphere are quite similar to the basic terms of the circle that's rotated to form the sphere. Say the center of the circle is named O and the radius is R. Now, when the circle is rotated about its diameter, the center of the circle O becomes the center of the sphere and the radius of the circle R becomes the radius of the sphere. So basically, the radius of a sphere is just the constant distance between its center and any point on its surface. Loosely speaking, the radius of a circle and the radius of a sphere are related in that they are both constant distances from the center to the outer boundary of the respective shape. So, the only length that we need to care about in case of a sphere is its radius. Now, we know that the diameter of a circle is just the line segment that passes through its center and whose endpoints are on the circle. And its length is twice the radius of the circle. Quite similarly, the diameter of a sphere is just the line segment that passes through its center and whose endpoints are on the surface of the sphere. Here too, the diameter is twice the radius. So, now that we have learned the basic terms of a sphere, let's take a look at its surface. We can see that a sphere has only one surface which is entirely curved. So, for a sphere, the curved surface area and the total surface area refer to one and the same thing. But how do we find this area? Well, the actual derivation is not very simple and requires knowledge of calculus, a branch of mathematics which you will be exploring only in your higher classes. For now, we can perform a simple experiment which is sort of a workaround for finding the surface area of a sphere. Ever seen someone play with the top? You must have seen them winding the string around the top something like this. Now, we need to do the same with a sphere. So, let's take a spherical ball of radius r and then wind a non-stretchable string around it completely like this. We need to ensure that there's no gap on the surface left and that the string is wound perfectly without any overlapping whatsoever. Wow, that's pretty neat. Now, on a piece of paper, we need to draw 4 circles, each with the same radius as the sphere, that is r. So, the 4 circles are ready. All we need to do now is start filling them one by one with the string we had wound around the ball. It's a tedious task, but eventually we will see that the string completely fills the 4 circles and has no part left. Pretty interesting, isn't it? We saw that the string, which had completely covered the surface area of the sphere, has been used to completely fill the regions of the 4 circles, each with the same radius as the sphere. So, what do we infer from this experiment? We infer that the surface area of a sphere of radius r is 4 times the area of a circle of radius r. Now, the area of a circle of radius r is pi r squared. Then, the surface area of a sphere of radius r is 4 times pi r squared, which is the same as 4 pi r squared. There you have it, the formula to find the surface area of a sphere. Now, the method we use to find the surface area is pretty common and is used very frequently. But since you have tuned into Tutorix, you deserve something special. I will help you memorize this formula using a very interesting visualization. But you need to promise me that you will take it only in the spirit of mathematical playfulness. Say, we have a sphere that's covered neatly in a perfectly thin wrapper. Now, the wrapper is opened in a very specific way such that it forms the curved surface of a cylinder having the same radius and the same height. Evidently, the surface area of the sphere would be the same as the curved surface area of this cylinder. And if we cut this curved surface laterally, we would get an even simpler shape, a rectangle. So, summarizing, the surface area of the sphere would be the same as the area of this rectangle. Now, to find the area of this rectangle, we first need to know the length of its 2 sides. This side would be the same as the height of the cylinder, right? And the height of the cylinder is the same as that of the sphere. Now, clearly, the height of a sphere is just the length of its diameter. The radius is taken as r, so the diameter is 2r, which means the height of the cylinder and the length of this side of the rectangle is 2r. Now, this other side of the rectangle, when rolled, forms the circumference of the circular edge of the cylinder. And the radius of the cylinder is r, so the circumference of this circular edge would be 2 pi r, which means that this remaining side of the rectangle is also 2 pi r. Therefore, the area of this rectangle is just the product of its sides, that is 2r into 2 pi r, which simplifies to, correct, 4 pi r squared. Now, we didn't really need to cut open the curved surface of the cylinder to form the rectangle, because we know the formula to calculate the curved surface area of a cylinder directly. It's 2 pi r h, where r is the radius of the cylinder and h is its height, which is 2r here. So, the curved surface area of the cylinder would be 2 pi into r into 2r, which again simplifies to 4 pi r squared. I didn't go directly for the formula because I wanted you to visualize the concept at the simplest level. Wasn't that pretty amazing? We learned 2 ways of memorizing the formula of the surface area of a sphere. The first was that the surface area of a sphere is 4 times the area of a circle of the same radius. And the second was that the surface area of a sphere is the same as the curved surface area of the cylinder that has the same radius and the same height. Now, if we are talking about the same sphere in these 2 examples, the combined area of these 4 circles should be the same as the curved surface area of this cylinder, right? But how do we visualize this? Okay, let's imagine this curved surface of the cylinder being cut open laterally and flattened out to form this rectangle. And then let's imagine each of these circles being unwrapped to form a triangle of height r and an unchanged area, that is pi r squared. All that we need to do now is align these triangles on this rectangle. Voila! It's a perfect match. So now we can safely say that the surface area of a sphere is nothing but 4 pi r squared. So now that we have quite some idea about spheres, I have a question for you. What do we mean by a hemisphere? A sphere cut in half. Precisely. Hemi in Greek just means half. So a hemisphere is just a solid sphere sliced right through the middle with a plane passing through its center. Now, what do you think would be the curved surface area of this hemisphere? Since it's half a sphere, that is both halves are congruent, shouldn't the curved surface area of this hemisphere just be half of that of a sphere? As a matter of fact, it is. So, the curved surface area of a hemisphere is just half of 4 pi r squared, which simplifies to 2 pi r squared. But what about the total surface area of a hemisphere? Well, the total surface area of a sphere is the same as its curved surface area because a sphere is nothing but a completely curved surface. That is, it has no base. But such is not the case for a hemisphere because a hemisphere has a curved surface and also has a base. So the total surface area of this hemisphere would be the sum of the areas of the curved surface and the base. Now, the area of the curved surface we just found out is 2 pi r squared and the base is nothing but a circular disc of radius r. So its area would be pi r squared. Then the total surface area of a hemisphere is just 2 pi r squared plus pi r squared, which gives us 3 pi r squared. So remember, the total surface area and the curved surface area of a sphere is 4 pi r squared. But the curved surface area of a hemisphere is 2 pi r squared and its total surface area is 3 pi r squared. I'm pretty sure that from now you'll start seeing spheres from a whole different perspective. However, you must remember that we can't really cut open the surface of a sphere and make a cylinder out of it. Neither can we unwrap a circle and make a triangle without changing the area. We just did it in mathematical playfulness so that we can visualize how the formula works. And now that we know the formula, what's the next logical step? To use it and solve problems, right? So in the next video, we'll be doing just that. For now, let's quickly summarize and I'll see you in the next one. So in this video, we got to understand spheres and hemispheres better. We saw that a circle can be rotated about its diameter to form a hollow sphere, and a circular disc can be rotated about its diameter to form a solid sphere. The radius of a sphere is just the constant distance from its center to any point on its surface. The diameter of a sphere, just like that of a circle, is twice the radius of the sphere. For a sphere of radius r, its total surface area and curved surface area are the same, that is 4 pi r squared. The surface area of a sphere is the same as 4 times the area of a circle of the same radius. Also, the surface area of a sphere is the same as the curved surface area of a cylinder of the same radius and the same height. A hemisphere is a solid sphere sliced right through the middle with a plane passing through its center. The curved surface area of a hemisphere is given by 2 pi r squared and its total surface area is given by 3 pi r squared. Here r is just the radius of the base.